Let's dive deeper into another technique that's particularly close to you, the Starshade project.
Starshade. Mm-hmm.
In 1962, Lyman Spitzer had published a paper titled The Beginnings and Future of Space Astronomy, where he proposed this occulting disk in front of a telescope. But for some reason, this idea never gained momentum until you brought it to life again. What is this idea, the concept of the occulting disk in front of the telescope? And then what is the Starshade project? What is the science and engineering or the design aspects behind it?
Yes. Well, it is my favorite and a favorite way to think about finding another Earth is to send a telescope above the blurring effects of Earth's atmosphere to see the planets directly. But remember, we were talking about the decimal places we have to go to? We would have to block out like a sun-like starlight to 1 part in 10 billion, billion, because our sun is 10 billion times brighter than our Earth is at visible wavelengths. Now, that's not easy. Remember, we're saying like if you're going to build a deck or whatever you're going to do, you're not going to be measuring. Like, I don't know if you've ever done anything to 10 decimal places. Never. Okay. I mean, most people why would you? It's just insane. So it's very hard to do. So there's many ways to do it. But one way is to put up a giant screen attached to its own spacecraft. And it's literally just like blocking out the light so you can see the starlight, so you can see the planet light directly. Now, imagine for a moment you put up a big spherical screen, like a big circle, and you block out the point of light that is the star. In the end, you know what happens? You're not blocking out the light because light can act like a wave. And that light waves by, it hits the edges of a giant screen, and it makes ripples in your image. So if you were to put a giant screen in space and work with a space telescope and snap a photo, like snap literally an image, you would see ripples like rings of light. It's like dropping a pebble in a pond. You've done that. You see ripples, waves, just waves like that. Now, Starshade is a very special shape. Lyman Spitzer back in the 60s figured out what shape does it have to be, not a giant circle like a disk. It has to be a flower-shaped pattern. And you know what happens? Then the light acts like a wave. It hits the edges of this special pattern and interacts with itself. It would be like dropping a pebble in a pond, but now the pond is perfectly smooth to 1 part in 10 billion. And all the waves are pushed to the outer edges. It's just amazing that he came up with this idea. And you know what? It's just hard to build. So every decade since Lyman Spitzer, it has been revived, actually. And it's an incredible idea. It's been matured by NASA. It's basically ready to go.
What are some of the engineering challenges involved with sending this giant flower-shaped shield into space and then making it completely in sync with this telescope?
Right. Well, in the 2010s, when I took over in 2013, and after my concept study wrapped up, the NASA team asked that question, like in really concrete terms. What are our 5 hardest problems, and solve them? We solved all of them. One of them is the shape. Like to get to 1 part in 1 part in 10 billion, it has to be a very precise shape, and you have to show you can build something in that shape. And that's what the pedal is on my wall. You should get a picture later. It was one of the early Starshade pedals made for demonstrating manufacturing tolerances. If Starshade has to be made to 4 decimal places in its shape, you have to be able to measure that and prove you can do it. So that's one of them. Another one is how to stow and deploy Starshade. Starshade is tens of meters in diameter. And the pedal on my wall is a full-scale pedal. And I have something to show you for a moment here. The Starshade, the 1% scale model.
Right.
Isn't it beautiful?
Looks amazing.
Well, now I want you to imagine this being 100 times bigger. So it's big. And by the way, the shape has to be so precise. Literally, I've had people get, like, this is so sharp and pointy, you can draw blood. And you know what else? If you have genes, it'll pick up a thread. You know how genes are so hard to destroy? Yeah. And in fact, one of the technology tall poles was the edges have to be so sharp, like our sun's light, not the starlight, but our sunlight could hit this and bounce into the, field of view. So the edges have to be literally like razor sharp to avoid that. Yeah. I'll just give you one more challenge. By the way, that 1% model was used in testing a scaled down version in the desert in Nevada, in Death Valley. And they went over a few kilometers in scale and put Starshade where it was to demonstrate that it can work.
Wow.
Yeah. So the other challenge you mentioned was in space, it has to be lined up almost perfectly, right? Because we have to block out starlight and not block out the planet light. So that is really hard as well. And we do a lot of docking at space station. We've done some formation flying in Earth's orbit. So we just had to show that really far away, where Starshade would operate, very far from Earth, there's almost no gravity. And we had to demonstrate that it boils down to a sensing problem. It's a bit technical to explain, but let's just say we demonstrated that we can achieve the formation flying precision necessary. Yeah.
What timelines are we operating on? When does the Starshade project launch? And then which exoplanets are you targeting first?
Good question. Well, we would target the nearest brightest sun-like stars, and we have a list. We have our favorite list. There's about a dozen stars that are prime for this. And Starshade could come in many sizes and work with many different telescopes. I hate to break this bad news to you right now. Remember, before I said Starshade has been started in the 1960s. It's been revived every decade. Sometimes it's put on the shelf for a while. And unfortunately, NASA has decided right now to not pursue Starshade as their first choice for finding another Earth. But I and some others, we're keeping Starshade alive, so the knowledge is still maintained. And you can go to projectstarshade.com and just follow where we're at whenever you check it out. Yes.
What's the first choice now?
Well, the first choice right now is called a coronagraph. It is a object. It's like a starshade, kind of, if you want to think about that, but inside the telescope.
Right.
And so the pros of that are you're only launching one thing, one telescope, not a telescope, and secondly, a starshade. So it seems simpler. The negative of that is that in order to block out the light when something's inside the telescope has to be perfect. And any little defect, light bounces around and mixes up. I just want to give you my analogy for it because we're really excited about our analogy. Let's imagine you have come to my office with a gift of banana bread, let's say.
Okay.
And you bring it to me and tell me the ingredients. Because you know how people are like allergic to everything these days? Isn't everyone like you go to a restaurant and they have this problem and that problem? Okay.
Yeah.
Let's say I don't eat cinnamon. And I'm like, oh, is there cinnamon in this? And you're like, yes. I'm like, okay, well, I'm going to need you to take all the cinnamon out. Now you have 10 billion parts flour and 1 part in 10 billion. So 10 billion, grains of flour. And no, you have 1 part per 10 billion cinnamon. So it's going to be pretty hard to pick it all out, right? But you probably could if you had to. Yeah. I'm sure you could go around MIT and find like a sophisticated chemical analysis tool and somehow separate it. Okay. We would do our best. Well, let's imagine you let me know in advance. Hey, I'm coming. I'm bringing you this banana bread. And I say, oh, by the way, I don't eat cinnamon. Can you please keep it separated before you mix it together? You'd be like, sure. And you bring the cinnamon and you can put cinnamon on yours. So with Starshade, we separate the light. It's like separating out the cinnamon. We separate the light, the planet light, before it enters the telescope. The coronagraph operates with the planet and starlight mixed together. They're all mixed together. And it's like picking out that cinnamon. Now you have to pick out the planet light. It's just a lot harder. It doesn't mean you can't do it. It's just harder. And you think you save because you only have the one telescope. You're not doing information flying. You're not doing some of the other complicated things, but you've translated all that complexity into having separated out the planet light at a later stage. And as that mixed light bounces off imperfections, it's really hard to disentangle. So your telescope has to be perfect.
If it has that limitation, then why has NASA picked that as their first choice?
I mean, I think that's a question you have to ask NASA.
I would. That's my next question. And my list of questions, the first one I'm going to ask.
Sure. But there's always trades and there's always back and forth. In astronomy, people have taken pride that every decade in the US, there's a committee that gets assembled to do a priority rank ordered list of what should we do. And indeed, the search for another Earth from space came at number 1. But because everyone has to work together, everybody's got to be on board together. We could have done Starshade with a small telescope. It's so efficient. It's so efficient at observing. It can observe all wavelengths together, unlike the coronagraph. And it just turns out that it's so efficient we could have a small telescope. But you know what? For the rest of the astronomers, they don't want a small telescope. They want a big telescope. And the coronagraph is easier. People, there's a bit of misinformation out there, but people thought it's easier to put a coronagraph with a big telescope than a Starshade with a big telescope. So it kind of, I think, went from there. It went from, it started in the right place. It started in a place that most astronomers want a big telescope. Starshade is better and can get away with a small telescope. So I think there's just a lot of decisions. I'm sure you've worked or people work in large groups and you don't always come up with the optimal solution for each interest. And that's what happened.
I believe you coined the term coronagraph as well with your colleague, David.
Actually, don't. No, I did not. I can tell you where the term coronagraph came from, though, which I'd like to.
Sure.
Have you been lucky enough to see a solar eclipse, a total solar eclipse?
Not a total one,
okay.
Fortunately.
Okay. I want you to try to see the next, anyone listening, a total solar eclipse in the coming years. You know, there's one coming up in Spain, I think in 2026.
Yeah, I think Egypt would also have
Egypt as well, yeah. Egypt. Oh, wow. Imagine seeing that with the pyramids. And the total eclipse, we're not talking about partial here. Now, when you see the total eclipse, what is amazing is you're blocking out the sun. Well, the moon is blocking out the sun, and we can see the corona. It sounds like crown. Like the sun has this plasma that's shooting off of it. But when the sun is there, it's so bright, we can't see the corona. When the sun is blocked, we can see the corona. Now, back in the 1920s, a French optical physicist named Leo, he wanted to see the corona anytime. It's very hard to see in a solar eclipse. You know, it has to be nearby. The sky has to be clear. So he invented a device he put inside the telescope. He called it a coronagraph. Yeah. So he can see it anytime. And now we've borrowed that term, the whole community, to call coronagraph something that blocks out starlight, not just our sun's light.